Welcome! Today, we'll explore an exciting coding problem: subarray sums divisible by k. This problem challenges us to find the number of subarrays whose sums are divisible by a given integer. Let's dive in and break it down step by step. In this problem, we are tasked with finding the number of subarrays within a given integer array, nums, whose sums are divisible by a given integer k. A subarray, as a reminder, is a contiguous sequence of elements from the array, and it must contain at least one element. The sum of a subarray is simply the sum of all the elements within that subarray. For a sum to be divisible by k, it means there exists an integer x such that the sum modulo k equals 0. For example, if a sum is 10 and k is 5, 10 is divisible by 5 because 10% 5 equals 0. The input consists of an array nums, which can be as large as 100,000 elements long, with each value ranging from -10,000 to 10,000, and an integer k, which can range from 2 to 10,000. The output will be a single integer representing the count of subarrays that satisfy this divisibility condition. Let's explore some examples to better understand this problem. Consider the first example where nums is 4, 5, 0, -2, -3, 1, and k is 5. The output is 7, indicating there are 7 subarrays whose sums are divisible by 5. Let's break them down. The entire array itself has a sum of 5, which is divisible by 5. The subarray 5 has a sum of 5, and 4, 5 has a sum of 9, which leaves a remainder of 4 when divided by 5 but becomes divisible when considering previous sums. Similarly, 0 has a sum of 0, which is divisible by 5. Another example is -2, -3, which sums to -5, divisible by 5. Extending this subarray to include 1, we get -2, -3, 1, whose sum is -4. This is divisible by 5 when the modulo operation is applied. Finally, 4, 5, 0 sums to 9, and again, this is divisible by 5 after considering the modulo. This example highlights how subarrays of various lengths, from single elements to the entire array, can contribute to the count. Now let's take a look at another example. Here, nums is 5, 10, 15, and k is 5. The output is 6, which means there are 6 subarrays whose sums are divisible by 5. Breaking it down, the individual elements 5, 10, and 15 are all divisible by 5. Then, the subarray 5, 10 has a sum of 15, which is divisible by 5. Similarly, 10, 15 sums to 25, also divisible by 5. Finally, the entire array 5, 10, 15 has a total sum of 30, which is divisible by 5. This example demonstrates how we can combine smaller subarrays to form larger ones while still satisfying the divisibility condition. In this third example, nums is 1, 2, 3, and k is 3. The output is 2, meaning there are 2 subarrays whose sums are divisible by 3. The first is 3, a single element subarray that is clearly divisible by 3. The second is 1, 2, which has a sum of 3 and is also divisible by 3. This example is simpler than the previous ones but underscores an important point: not all subarrays will meet the condition, and the solution must efficiently identify only those that do. It's also worth noting that the constraints for this problem allow nums to contain both positive and negative integers, which can affect how we calculate modulo results. Finally, let's discuss some important edge cases to consider. First, if nums contains only a single element, we need to check if that element is divisible by k. For instance, if nums is 5 and k is 5, the output would be 1 because the single element itself forms a subarray that satisfies the condition. Another case is when all elements in nums are 0. Here, every possible subarray will have a sum of 0, which is divisible by any k. For example, if nums is 0, 0, 0, and k is 5, the output is 6 because there are 6 possible subarrays. Handling large input sizes efficiently is another critical aspect. With up to 100,000 elements, the solution must avoid brute force approaches and use optimized algorithms. Lastly, we must account for negative numbers, as these can affect the modulo operation. For example, if nums is -2, -3, and k is 5, the sum of -5 is still divisible by 5. These edge cases highlight the importance of designing a robust solution capable of addressing all scenarios within the problem's constraints. To solve the problem of finding the number of subarrays whose sums are divisible by k, we looked into multiple approaches. One straightforward method is the brute force approach, which uses a sliding window with nested loops. The intuition here is to calculate the sum of every possible subarray and check if it's divisible by k. To do this, we iterate through all possible starting points of subarrays with an outer loop, and for each starting point, the inner loop calculates the sum for all possible ending points. If the sum is divisible by k, we increment our count. While this method is simple and easy to implement, it has a significant drawback. Its time complexity is n squared, because of the nested loops, which makes it inefficient for large arrays. However, it does have the advantage of requiring no additional space beyond the input array, with a space complexity of 1. This trade-off makes it less suitable for handling large datasets in practice. Now, to improve efficiency, we considered an optimized approach using prefix sums combined with modulo operations and a hash map. The key idea here is to avoid recalculating the sum for every subarray by maintaining a running prefix sum. Instead of focusing on individual subarray sums, we calculate the remainder when the prefix sum is divided by k. This is where the hash map comes into play. Subarrays that leave the same remainder when divided by k have sums that differ by a multiple of k, meaning their difference is divisible by k. To implement this, we iterate through the array to compute the prefix sum, calculate its remainder modulo k, and check if the same remainder has been seen before. If it has, it indicates a valid subarray. The hash map tracks the frequency of each remainder, and we initialize it with 0 mapped to 1 to handle cases where the prefix sum itself is divisible by k. This method has a time complexity of n, since the array is traversed only once, and a space complexity of k, due to the storage of remainders in the hash map. While it's slightly more complex to implement, it's far more efficient for larger arrays. The key insight that makes the optimized approach work lies in the relationship between subarray sums and remainders. If two prefix sums leave the same remainder when divided by k, the difference between those sums must be divisible by k. This observation allows us to use a hash map to efficiently track the count of remainders and identify valid subarrays in a single pass through the array. One important detail to handle carefully is negative remainders. When performing modulo operations, negative remainders can occur, so we normalize them into the range of 0 to k1 to ensure consistency. With these observations, we chose the optimized approach over brute force. While the brute force method has its merits in simplicity, it's impractical for large inputs due to its n squared time complexity. The optimized approach, on the other hand, reduces the time complexity to n, while requiring only minimal additional space. This makes it particularly suitable for competitive programming scenarios and real-world applications where performance and scalability are critical. The trade-off between time and space here is well justified, given the significant performance gain. The optimized approach represents an excellent balance between computational efficiency and implementation complexity. By leveraging prefix sums, modulo operations, and a hash map, we achieve a solution that is both fast and scalable. It transforms the problem into one that can be solved in linear time while maintaining an easy-to-understand structure. This makes it the preferred solution for this problem, particularly when dealing with large datasets. Overall, the approach is practical, efficient, and strikes the right balance, making it the ideal choice for solving the challenge of subarray sums divisible by k. To solve this problem, we need to determine the number of subarrays within the given array whose sums are divisible by a specified integer, k. A subarray is simply a contiguous segment of the array. For instance, in the array 4, 5, 0, -2, -3, 1, and k equals 5, there are 5 such subarrays, 5, 5, 0, 0, 0, -2, -3, and -2, -3, 1. The key to solving this efficiently is to recognize that if the sum of a subarray is divisible by k, then the cumulative sum of the elements up to that point must leave a remainder of 0 when divided by k. Furthermore, if two cumulative sums produce the same remainder when divided by k, their difference must also be divisible by k. Using this insight, we can leverage prefix sums and modulo arithmetic to determine these remainders as we iterate through the array. Instead of storing the cumulative sums directly, we store their remainders modulo k and track how often each remainder appears using a dictionary. This will allow us to count the valid subarrays efficiently as we progress through the array. Finally, we initialize the dictionary with 0, 1 to account for cases where the cumulative sum itself is divisible by k, and we maintain two variables, one for the cumulative sum and another to store the count of valid subarrays found so far. Now that we have our data structures initialized, we iterate through the array to process each element. For every element, we first add it to the cumulative sum to update the running total. Then, we calculate the remainder of this cumulative sum when divided by k. If the remainder turns out to be negative, we adjust it to fall within the range 0, k1 by adding k to it. This adjustment ensures consistency in how we handle remainders, particularly when negative numbers are involved. Next, we check if this remainder already exists in our dictionary, remainder_count. If it does, it means there are subarrays ending at the current index whose sums are divisible by k. The number of such subarrays corresponds to the frequency of this remainder in the dictionary. We add this frequency to our total count. Finally, we update the dictionary by incrementing the count of the current remainder. Once the iteration is complete, the total count holds the number of subarrays whose sums are divisible by k, and we return this value as the result. This approach works so efficiently because it leverages key insights about remainders and prefix sums. By focusing on remainders, we avoid the need to compute the sums of all possible subarrays explicitly, which would be computationally expensive. Instead, we use modulo arithmetic to simplify the problem. One important detail is how we handle negative cumulative sums. Since the modulo operation can produce a negative remainder, we adjust it to ensure it always falls within the range 0, k1. This adjustment guarantees that our calculations remain consistent. Prefix sums are also an essential part of the optimization, as they allow us to reuse previously computed sums to derive new subarray sums. In terms of data structures, we use a dictionary to store the frequency of remainders, which enables fast lookups and updates in constant time. Additionally, we maintain two simple variables, one for the cumulative sum and another for the count of valid subarrays. The time complexity of this solution is O(n), where n is the length of the array, because we iterate through the array once. The space complexity is O(k), as the dictionary will store at most k unique remainders, making this approach both efficient and scalable. To see how this algorithm works in practice, consider the example array 4, 5, 0, -2, -3, 1, with k equals 5. We start by initializing the dictionary remainder_count with 0, 1, and both cumulative_sum and count are set to 0. As we iterate through the array, we first encounter the element 4. Adding it to the cumulative sum gives 4, and the remainder is also 4. We update the dictionary to 0, 1, 4, 1. Next, we process the element 5, which brings the cumulative sum to 9. The remainder is 4, and since this remainder has already been seen once, we add 1 to our count, making it 1. The dictionary is updated to 0, 1, 4, 2. With the element 0, the cumulative sum remains 9, so the remainder is still 4. This remainder has now occurred twice before, so we add 2 to our count, bringing it to 3. We then update the dictionary to 0, 1, 4, 3. Moving on to -2, the cumulative sum becomes 7, and the remainder is 2. We update the dictionary to 0, 1, 4, 3, 2, 1. For -3, the cumulative sum reaches 4, and the remainder is 4 again. This remainder has occurred 3 times already, so we add 3 to our count, making it 6. The dictionary becomes 0, 1, 4, 4, 2, 1. Finally, the element 1 brings the cumulative sum to 5, with a remainder of 0. Adding 1 to the count gives a final result of 7. The dictionary is updated to 0, 2, 4, 4, 2, 1, and we return 7 as the total number of valid subarrays. When implementing this algorithm, it's important to consider a few edge cases. For instance, if the array consists entirely of zeros, every single subarray will have a sum divisible by k. The total number of subarrays in this case is n asterisk, n plus 1/2, where n is the length of the array. Another edge case involves negative numbers, which can produce negative remainders during the modulo operation. To handle this, we ensure that remainders are adjusted to fall within the range 0, K1. Finally, if the input array is empty, there are no subarrays to consider, so the result should simply be 0. By addressing these scenarios, we can ensure that the solution is robust and handles all possible inputs correctly. This Python implementation solves the problem of finding subarrays whose sums are divisible by a given integer k. The solution uses the concept of prefix sums and their remainders modulo k to detect divisible subarrays efficiently. The function begins by initializing a dictionary remainder_count to store the frequency of prefix sum remainders. The value 0, 1 is preset to handle cases where the prefix sum itself is divisible by k. A prefix_sum keeps track of the running sum of array elements, and result stores the count of valid subarrays. The function then iterates through each number in the input array. For each number, it updates the prefix sum and calculates its remainder modulo k. If the remainder is negative, it is adjusted to be within the range 0, K1 by adding k. Next, the function checks if the current remainder has been seen before in the remainder_count dictionary. If it has, this means there exists a previous prefix sum with the same remainder, and the subarray between these two prefix sums is divisible by k. The count of such remainders is added to the result. Finally, the frequency of the current remainder is updated in the dictionary to reflect its occurrence. This approach ensures an efficient O(n) time complexity since it processes the array in a single pass and uses a dictionary for constant time lookups. This makes it well suited for large input arrays. Here, we start by importing the necessary libraries and creating our solution class. The goal of this method is to find the count of subarrays whose sums are divisible by a given integer k. To achieve this, we utilize a hash map to store the frequency of prefix sum remainders when divided by k. This helps us efficiently track how often a particular remainder occurs. Initially, the map is seeded with a single entry where the remainder 0 has a frequency of 1. This accounts for cases where the prefix sum itself is divisible by k. Next, we declare two variables, prefix sum, which will keep a running total of the elements in the array, and result, which will store our final count of valid subarrays. The for each loop then iterates through each number in the input array. For each number, we update the prefix sum by adding the current number. After that, we compute the remainder of the updated prefix sum when divided by k. If the remainder is negative, we adjust it by adding k to ensure it falls within the range of 0 to k1. This normalization is necessary for consistent handling of remainders across all cases. At this point, if the current remainder already exists in the map, it means there are subarrays ending at the current index whose sums are divisible by k. We increment our result by the frequency stored in the map for this remainder. Now, we update the frequency of the current remainder in the hash map. If the remainder is already present, we increment its count, otherwise, we initialize its count to 1 using the getOrDefault method. This ensures that the map accurately reflects the number of times each remainder has occurred up to the current index. After processing all the elements in the array, the variable result holds the total count of subarrays whose sums are divisible by k. Finally, we return this result as the output of the method. This approach efficiently calculates the desired count in O(n) time complexity, where n is the length of the input array, thanks to the use of prefix sums and the hash map for constant time lookups. By leveraging the properties of remainders and modular arithmetic, we avoid the need for nested loops, making our solution optimal and scalable for larger inputs. To solve the problem, we use a combination of prefix sums and a hash map to keep track of remainders. Let's start with the array nums equals 4, 5, 0, -2, -3, 1, and k equals 5. Initially, we set up our variables, remainder_count as 0, 1, to account for subarrays starting from the beginning, prefix_sum as 0, and result as 0. Now, for the first number, 4, we add it to our prefix_sum, which becomes 4. The remainder when dividing 4 by 5 is also 4. Since this remainder is not in our hash map, we add it, so remainder_count becomes 0, 1, 4, 1. The result remains 0 because this is the first time we've seen this remainder. Next, for 5, adding it to prefix_sum gives 9. The remainder of 9% 5 is 4, and since 4 already exists in remainder_count with a count of 1, we add this count to result, making it 1. We then update remainder underscore count to 0, 1, 4, 2. For the next number, 0, adding it to prefix underscore sum keeps it at 9, and the remainder remains 4. This time, 4 has a count of 2 in the hash map, so we add 2 to result, making it 3. We then update the hash map to 0, 1, 4, 3. Moving on to dash 2, adding it to prefix underscore sum results in 7. The remainder of 7% 5 is 2, which is new, so we add it to the hash map, resulting in 0, 1, 4, 3, 2, 1, while result remains 3. For dash 3, the updated prefix underscore sum is 4, and the remainder is 4. Since 4 appears 3 times in the hash map, we add 3 to result, making it 6. Finally, for 1, adding it to prefix underscore sum gives 5 with a remainder of 0. The remainder 0 exists in the hash map with a count of 1, so we add 1 to the result. The final result is 7, which is the total number of subarrays whose sums are divisible by 5. Now, let's look at a simpler example where nums equals 1, 2, 3, and k equals 3. Once again, we initialize remainder underscore count as 0, 1, prefix underscore sum as 0, and result is 0. Starting with the first number, 1, adding it to prefix underscore sum makes it 1. The remainder of 1% 3 is 1, which is new, so we add it to the hash map, resulting in 0, 1, 1, 1. The result remains 0. Next, for 2, adding it to prefix underscore sum gives 3, and the remainder of 3% 3 is 0. Since 0 already exists in remainder underscore count with a count of 1, we add 1 to result, making it 1. We then update remainder underscore count to 0, 2, 1, 1. For the final number, 3, adding it to prefix underscore sum results in 6, and the remainder of 6% 3 is 0. This time, 0 exists in the hash map with a count of 2, so we add 2 to result, making it 3. The final result is 3, which means there are 3 subarrays in this example whose sums are divisible by 3. Finally, let's consider the example where nums equals dash 1, 2, 9, and k equals 4. As before, we initialize remainder underscore count as 0, 1, prefix underscore sum as 0, and result is 0. For the first number, dash 1, adding it to prefix underscore sum results in dash 1. The remainder of dash 1% 4 is 3 because in modular arithmetic, we adjust negative remainders to be positive. Since 3 is new, we add it to the hash map, updating remainder underscore count to 0, 1, 3, 1. The result remains 0. Next, for 2, adding it to prefix underscore sum gives 1, and the remainder of 1% 4 is 1. This remainder is also new, so we add it to the hash map, resulting in 0, 1, 3, 1, 1, 1, while result stays at 0. Finally, for 9, adding it to prefix underscore sum gives 10, and the remainder of 10% 4 is 2. This is another new remainder, so we add it to the hash map, making it 0, 1, 3, 1, 1, 1, 2, 1. The result remains 0 since no remainders were repeated. The final result for this example is 0, meaning there are no subarrays whose sums are divisible by 4. To analyze the time complexity of our solution, let's break it down step by step. First, we handle initialization. Setting up the dictionary remainder underscore count with an initial entry, 0, 1, is a constant time operation, or O1. Similarly, initializing the variables prefix underscore sum and result also takes constant time. Next, we iterate through the array nums using a single for loop. If the size of the array is n, this loop runs exactly n times, making its contribution O, n. Within each iteration, we perform several operations. Updating the prefix underscore sum by adding the current element is a simple addition, which is O1. Calculating the remainder of dividing prefix underscore sum by k also takes constant time. If the remainder is negative, we adjust it by adding k, which is another O1 operation. Finally, we access and update the dictionary remainder underscore count. Since dictionaries in Python are implemented as hash tables, these operations are O1 on average. All these steps within the loop are constant time operations, so the total time complexity of the loop remains O(n). Since the for loop dominates the time complexity, the final computation step, which involves simply returning the value stored in result, is negligible. Returning a single variable is an O(1) operation. Therefore, when we combine all the steps, the overall time complexity of our solution is O(n). This is because the loop processes each element in the array exactly once, and all the operations inside the loop are constant time. This makes our algorithm highly efficient for large input sizes, as its runtime grows linearly with the size of the input array nums. Now, let's look at the space complexity of the solution. The primary contributor to space usage is the remainder_count dictionary, which keeps track of the frequency of remainders when dividing the prefix_sum by k. In the worst-case scenario, there can be at most k unique remainders, ranging from 0 to k1. This means the dictionary requires k space. Apart from the dictionary, the algorithm uses a few additional variables, prefix_sum and result, both of which occupy constant space, or O(1). Since these variables do not depend on the size of the input array, their contribution to the space complexity remains constant. Therefore, the overall space complexity of the solution is O(k), dominated by the dictionary. Importantly, this space requirement is independent of the size of the input array nums, which ensures the algorithm is memory efficient for larger arrays. To appreciate the efficiency of our approach, let's compare it with the naive brute force solution. In the brute force method, we would calculate the sum of all possible subarrays and check if each sum is divisible by k. For an array of size n, there are n² subarrays, and calculating the sum of each subarray could take up to O(n) operations. This results in an overall time complexity of O(n³), which is highly inefficient for large inputs. In contrast, our optimized solution reduces the time complexity to O(n) by using the prefix sum and remainder frequency map. The key insight here is that if two prefix sums yield the same remainder modulo k, the subarray between those indices is divisible by k. This eliminates the need to compute the sums of subarrays explicitly, making the algorithm much faster. Moreover, the best, average, and worst-case time complexities remain O(n). This consistency is due to the fact that the for loop and dictionary operations maintain their efficiency regardless of the input distribution. While dictionary operations could theoretically degrade to O(n) in rare cases of hash collisions, this is unlikely in practice, so the overall efficiency is reliable. To mathematically confirm the big O complexity, consider how the algorithm processes the input. Each element in the array is visited exactly once, and a constant amount of work is done for each element. This ensures the time complexity is O(n). Additionally, the dictionary remainder_count is used to store remainders modulo k. The size of this dictionary is at most k, meaning the space complexity is O(k). Importantly, neither the time nor space complexity depends on the specific values within the array, they depend only on the size of the array and the divisor k. This shows that our solution is both time optimal and space efficient for this problem, achieving the best possible performance given the constraints. Let's talk about some common mistakes that can trip you up when solving this problem. First, not handling negative remainders correctly is a frequent issue. In some programming languages, like Python, the result of a modulo operation can be negative if the dividend is negative. This can break the logic of counting subarrays because the remainder needs to be consistent. To fix this, you should normalize the remainder by adding k to it and then taking modulo k again. This ensures the remainder is always non-negative. Another common mistake is using brute force on large inputs. A naive approach that iterates through all possible subarrays and calculates their sums has a time complexity of O(n²), or even O(n³). This is incredibly inefficient for large arrays, such as when n is greater than 10,000. Lastly, misinterpreting the problem statement can also cause errors. For example, you might forget to include subarrays of size 1 individual elements that are divisible by k. Overlooking these cases results in incomplete outputs and incorrect answers. Now, let's explore two more pitfalls. Overlooking the prefix sum optimization is another mistake that can lead to inefficiency. If you repeatedly calculate sums from scratch for each subarray, you'll end up doing a lot of redundant work, which increases the time complexity unnecessarily. Leveraging prefix sums and modular arithmetic is key to avoiding this issue. Another error is not initializing the frequency map correctly. The frequency map is used to track how often each remainder appears, and it needs to be initialized with a base case. Specifically, you should set frequent 0 equals 1 to account for subarrays starting from the very beginning of the array that are divisible by k. Without this initialization, these subarrays won't be counted properly, leading to incorrect results. When tackling this problem in an interview setting, there are a few important insights to keep in mind. First, recognize this as a classic example of using prefix sums combined with modular arithmetic to optimize subarray computations. Understanding the concept of remainder frequency maps is crucial for solving this problem and others like it. Also, be mindful of edge cases. For example, clarify with the interviewer whether the array can contain negative numbers and how those should be handled. Special cases like k being equal to 1 or arrays entirely composed of zeros require extra attention. Additionally, when discussing your approach, highlight the inefficiency of brute force and quickly transition to the optimized solution using prefix sums and hash maps. This demonstrates your ability to think critically about performance. Finally, be ready to discuss trade-offs. For instance, while the optimized solution uses extra space for a hash map, it drastically reduces time complexity, which is often the more important consideration in competitive scenarios. This problem also has connections to several related problems. For example, in LeetCode 560, subarray sum equals k, you use a similar approach with prefix sums and hash maps to count subarrays with a specific sum. Another related problem is LeetCode 523, continuous subarray sum, which involves checking if a continuous subarray sums to a multiple of k. Then there's LeetCode 992, subarrays with k different integers, which focuses on counting subarrays with exactly or at most k distinct integers, requiring a different optimization strategy but similar principles. Finally, LeetCode 1248, count number of nice subarrays, also involves counting subarrays based on specific properties and often benefits from optimization techniques like those used here. Exploring these problems can help reinforce the core concepts and prepare you for similar challenges. There are also alternative approaches to solving this problem, each with its own trade-offs. The most basic is brute force, which has a time complexity ranging from O(n) squared to O(n) cubed, depending on the implementation. While simple to write, this approach is only suitable for small input sizes due to its inefficiency. On the other hand, the optimal approach involves using prefix sums with a hash map, reducing the time complexity to O(n), and requiring O(k) space for the hash map. This trade-off between space and time makes it ideal for real-world applications and competitive programming. Lastly, there's the divide and conquer approach, which is rarely used for this problem. While it might be applicable in specific scenarios with unique constraints, it typically comes with higher complexity and additional implementation overhead. Understanding these trade-offs helps you choose the best method depending on the context and constraints of the problem. Great job! We reviewed an efficient solution to the subarray sums divisible by k problem. Remember the power of hash maps and modular arithmetic for solving problems like this. Keep practicing, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!